Welcome to G Fun Facts Online. Ever had your power go out? It's a pain, right? But imagine that single power outage also means your tap runs dry, your internet vanishes, and even your commute grinds to a halt. Sounds like a disaster movie, but it's a real concern in our modern world. Today, we're diving deep into something called cascading failures. It's all about how our essential services, the power grids, water supplies, communication networks, and transportation systems are intricately linked. When one of these critical infrastructures stumbles, it can trigger a domino effect, leading to widespread disruptions. Understanding this is super important if we want to keep our society running smoothly. So, let's talk about these connections. Critical infrastructures aren't lonely islands. They absolutely depend on each other. Think about it. A water treatment plant needs electricity to purify your water and pump it to your home. Power plants, on the other hand, might need huge amounts of water for cooling. Communication networks? They're the digital nervous system, crucial for coordinating almost everything else. And transportation systems? They're the arteries, moving fuel, equipment, and the people who keep everything operational. These relationships, which experts call interdependencies, come in a few flavors. First, there's physical interdependency. This is a direct link, like a power line feeding electricity straight to a water pump. Then there's cyber interdependency. This is all about the information and communication technology that controls and monitors these systems, the digital brains behind the operation. We also have geographic interdependency. This happens when different infrastructures are located close together, making them all vulnerable if a local hazard, like a flood or an earthquake, strikes. Finally, there's logical interdependency, which arises from policies, legal rules, or regulations that tie systems together. Now, these connections are great for efficiency when everything's humming along. But when trouble hits, say a hurricane, a major cyber attack, or even a big accident, these same connections become superhighways for failure. One problem can rapidly spread, causing a cascade across multiple sectors. And with climate change making extreme weather events more frequent and intense, these risks are only growing. So how do scientists and engineers try to get a handle on these complex chain reactions? The answer is modeling. They build sophisticated models to understand how these interdependent systems behave and to pinpoint their weakest links. There are several cool ways they do this. One popular method is using network-based models. Imagine our infrastructures as a giant social network, where each component is a person and the connections are friendships. These models analyze how the network reacts if some friends or components are suddenly removed. How does it affect everyone else they're connected to, and the systems connected to those systems? Then, there are system dynamics models. These focus on the feedback loops and how different parts of the infrastructure interact and influence each other over time. Agent-based models take a different approach. They simulate individual components as if they were tiny autonomous agents, each with its own rules and behaviors. The overall system behavior then emerges from all these tiny interactions, like watching an ant colony at work. A newer, really interesting technique is HLA-based co-simulation. HLA stands for High-Level Architecture. This method is like building with different, specialized Lego kits, one for the power grid, one for water, and so on, but ensuring all the pieces can still connect and interact. It allows for a very detailed look at each system, while still capturing how they impact each other, especially during big disasters. There are also input-output models, often borrowed from economics. These quantify how the output or service from one sector, like electricity, becomes an input for another, like a hospital. A specific type, the inoperability input-output model, looks at how a loss of function in one area impacts the functionality of others. And finally, optimization models use powerful math to identify which components would cause the most severe damage if they failed, or to figure out the best strategies to get things back online quickly. Now, building these models sounds like a perfect solution, but it's actually incredibly challenging. For starters, these infrastructures are mind-bogglingly complex and very different from each other. Getting accurate, complete data on all their components, how they're interconnected, and how vulnerable they are to different threats is often a huge hurdle. We're talking about real-time operational data and even knowing how strong or critical each dependency is. Plus, these systems aren't static. They change over time, especially during a crisis. And then there's the human factor. The decisions made by operators and emergency responders play a massive role in how a cascade unfolds and how quickly things recover. But that's really hard to put into numbers and equations. We also need to consider the wider impact. It's not just about broken pipes and down power lines. Infrastructure failures have real social and economic consequences, and understanding how these affect different groups of people is an ongoing area of research. So what's the ultimate goal of all this complex modeling? It's to enhance resilience. Resilience means the ability of these systems to withstand disruptions, adapt to them, and bounce back quickly. There are several key strategies to make our infrastructures more resilient. First and foremost, we need to accurately map and analyze all those connections between different systems. Then, these models can help us pinpoint the most critical components, the ones whose failure would trigger the biggest domino effect, so we can prioritize protecting them. We can also use simulations to test different recovery plans and figure out the best way to allocate resources to minimize downtime. Proactive measures are also key. This includes things like hardening infrastructure against known threats, building in redundancy, that's backups, and designing systems to be more flexible so they can adapt during a crisis. Improved information sharing is also vital. Governments, infrastructure operators, and researchers all need to collaborate and share data. And importantly, we need to consider those perfect storm scenarios, the low probability but high consequence events where multiple failures happen at once. Looking ahead, this field is constantly evolving. Future research will likely focus on developing even more sophisticated and integrated modeling techniques that can better capture the dynamic and diverse nature of these systems. There's a big push for improving how we collect, validate, and share data, perhaps even using high-quality synthetic data when real-world information is scarce. Models will also need to more explicitly incorporate the impacts of climate change and emerging threats like advanced cyber attacks. And there's a growing emphasis on integrating social and economic factors to get a truly holistic understanding of resilience and vulnerability. Crucially, we need to bridge the gap between these advanced scientific models and the practical needs of local planners and emergency managers who are on the front lines. By advancing our understanding of cascading failures through robust modeling, we can build more resilient critical infrastructures, ones that can weather the inevitable storms of our increasingly complex world, ensuring that the essential services we all rely on continue to flow. Of course, strong governance and partnerships between public and private organizations are absolutely essential to turn these scientific insights into real, effective actions that build that resilience. That's our deep dive for today on Fun Facts Online. It's clear that the systems that support our daily lives are more connected than we might think, and understanding those connections is the first step to keeping them strong. Thanks for tuning in.